Hi, I'm Rebecca Ringett from the Community Coordinated Modeling Center, here to tell you some more about our tool called Kamodo. As in the previous introduction video, I said it's an official NASA open source project. And here I'm going to start digging into what the tool can do and what it can offer you. This is going to be a series of demonstrations based on the notebooks available on our repository. Speaking of which, let's start by going to the repository. All right, so here you are. So all of the notebooks that I'm going to be walking through in this series are here, located in the Docs and Notebooks directory. So the first one to start with is one labeled Start Here, which I have open right here. So this is the beginner's tutorial to start understanding how to figure out what you want to do with the tool. Okay, so the first thing is to realize that the interface that you're looking at is an interface to model output data. And in order to figure out what you want to do with it, you got to choose what model output you want functionalized. Okay. So this assumes you already have model data output downloaded from the CCMC or from some other resource, and that model output is on this list and functionalized by Kamodo. All right, so the first thing to do is to import this model wrapper, which I call MW all the time. And you can use it to find out what models are currently functionalized. This is the current list as of December 2022. That list will be growing and is growing. You can access documentation in the normal way, help for the function, and read that in more detail as you wish. You can show all of the possible variables with this function, variable search, and by just giving it a blank string. And it will output all of the variables that have been functionalized in Kamodo across all of the models. So this list is quite extensive. But a lot of times you have a particular kind of variable in mind. In this case, let's think about temperature. Okay. Another option would be for neutral density or density. And it's the way you change it is to simply just change what the string is, and it goes for you. It finds all of the density variables that are available across all of the models. That list is also still quite extensive. Notice it has a model name and then followed by density. Also notice that it's pulling any description that has the word density in it. So this isn't just neutral density. This could also be current density as given by the SWMF model. Okay. I'm going to switch back to the temperature example and go with that. So there's a list of all of the temperature variables available in the currently functionalized model outputs. But a lot of times you already have a model in mind because you have retrieved that data from CCMC. So you can look for what variables are available for your chosen model with this syntax. If you want to see all of the variables just from CTP, you just give it a blank variable string and give it the model you want, and it prints it all out for you in reasonably formatted arrangement. So the first thing you see in all of these formats, you see something about the model at the top that changes based on how you execute this. Then you see the LaTeX representation of that variable in the data, followed by a list of objects here. The first thing in that list is a string. That string is a description of what the model is. Then you see an integer. You see the coordinate system here. This is GDZ, geodetic coordinate system, and spherical coordinates. And you see the variables in the coordinate system that the variable depends on. So in this case, it's time, longitude, and latitude. This particular variable is only 3 dimensions, so time plus 2 spatial. And then it's that list is concluded with the units here, kilo electron volts or keV. Once you have a data set on your computer, you can use that to figure out what variables are in that data set. So you just give it the, you can find out all of the variables in your given data set by giving it a blank string, the model that data set belongs to, where it came from, and where that's located. So in this case, it's CTP data, and it contains all of these variables. Okay. And you can figure out what temperature variables you have with similar syntax, just giving it the temperature string. And just for fun, you can see if there's any magnetic variables. And no, you don't get magnetic variables from CTP. You can also figure out what the time range is for the data that you have with this by calling the file times function. And it gives you a nice, neat printout. And if you set a variable here to return to accept the return values, you will get two datetime objects in UTC, corresponding to the beginning and end of that time range. Okay. So this particular function, this call right here, this file times, performs any pre-processing or file conversions needed for that model data set automatically. If you at a later time add or remove data from that directory, you need to remove the two text files generated by Kamodo in that directory and then proceed as normal. Because then it has to reset with the beginning and end times are. It has to reset the pre-processing so that you don't get the software breaking in the process. Okay. All right, so the way you import the correct model reader object is quite simple. You go mw.modelReader and tell it what model you want. It automatically pulls in the correct model reader. In this case, model is CTP, so it pulled in the CTP reader. Okay. You can easily functionalize all of the variables in the CTP data that you have by simply saying reader and giving it the location of the data. By default, it will create all of these functionalized variables. Quite a list here. A couple things to note. I'm going to expand this just to show you something. Okay, so I want you to note, say, let's take one particular function as an example. Best example is right here. So this neutral temperature. Notice there are 4 versions of this neutral temperature variable. First, there is a version that just depends upon this R vector. And you see from the subscript, it's in geodetic spherical coordinates, and it's based on 4 dimensions. So that means it's time, latitude, longitude, and vertical, not in that order. The gridded version of that variable, indicated by the ijk at the end, is indicated right below it. And now you get the different coordinates, just different coordinates that that variable depends on, all in a nice list and in the correct order. Notice that this iLev here is unitless, and that's the pressure level that that variable is directly dependent upon in the data itself. Now, when you're trying to figure out what the neutral temperature is at a particular height, you can't do that with this function because it depends on pressure level, not height. So what the model reader for CTP automatically does is it creates an alternate version of that neutral temperature function, dependent upon the pressure level inversion function, which now depends on height. Notice this Km in the subscript here. That tells you that it's still geodetic spherical coordinates in 4 dimensions, but instead of pressure level, it depends on height. The gridded version of this new neutral temperature function says that explicitly here, that it depends on height and that that height is in kilometers. That process is automatically executed in all model readers that have a variable dependent upon an internal coordinate system. In this case, that internal model-specific coordinate system is pressure level. So let me collapse this and we'll keep moving on. All right, so the next thing you can do with a Kamodo object is treat it a little bit like a pandas thing, like a pandas data frame, although it's not quite a pandas data frame. You can get the printed name of what that function is called. The subscripts, this particularly helps when you have more than one subscript in the name, as per what the name is in the code. And that isn't always obvious from this depiction here with the LaTeX. So this can be particularly useful for that. various options for the model reader. You can have there's an option called gridded int to return all of the requested variables, but without the gridded interpolator, without the IJK option. By default, it will automatically produce a gridded version of any function needed to do a custom coordinate conversion. So in this case, this pressure level inversion variable, because that is required for the calculations. The other options for the model readers include the variables requested option. If you set this option to a list of the variables that you want, it will only functionalize those variables and anything else needed for a custom coordinate conversion, such as shown here. Okay, I already talked about this. If you request a variable that's not possible in CTP, for the CTP data, it will give you an error. It won't break. If you request a variable that is possible through CTP but not in your data set, you'll get a not available message. You can combine the options I already discussed above. Say the variables requested, you want neutral temperature and ion temperature, but you don't want the gridded interpolators for whatever reason. You can do that and get only the pieces that you want. Each Kamodo object generated by a model reader has the file date attribute here. That file date gives you a datetime object corresponding to midnight of the first day of a given data set. This is important for comparing Kamodo objects generated for different model readers that could have data sets starting on different dates. What you will notice here, if you look at the coordinate ranges, here I have time, and it starts at 0.25 and goes up to 120. Scrolling back up just a little bit, you'll find out that that time is in hours. Well, hours since what reference point, you might ask? Should ask. The reference point is this file date here. So the time in hours for all of the functionalized model data sets are going to be since midnight of the first day of the data set. Right, that's the standard that we've implemented. The next thing that you can do with the functionalized data is to easily plot a four-dimensional data set in 2 dimensions. So notice that this neutral temperature variable, earlier in the data, it depends on pressure level. But remember, it automatically performs that internal model-specific coordinate conversion and offers you an alternate representation that depends on height instead of pressure level. And because it does that, you can plot based on height instead of pressure level. Alternatively, you can use the original neutral temperature variable, which would just have an iLev here. And you should copy that here. And instead of height, you would want pressure level. And that would be, let's say 5. And then run it for that. And that'll give you a 2-dimensional plot at this time slice and that pressure level slice. While that's running, I'll talk about the next one. This is the same plot that was in the previous block before I started running it for the other one. It's just a nicer version. You see a blank place in the plot here simply because the pressure level changes with location and time. And at that time, that height, this latitude, and hold on, and that longitude, that pressure level is not defined there. That's out of the range of the model data. So notice that up here, just by changing it to a different variable, different time, different pressure level slice, you can easily produce the same plot. Feel free to play with that. It's fun. You can also plot a one-dimensional slice for a given variable and multiple variables and plot them side by side using the syntax shown here. And you can play around with this too. You can change the time to be something different. You can change this to be, say, 300 instead of 350, run it again, and you get a new plot. All right. So here, it's important to mention the interpolation commands, and this is the real difference between the non-gridded functions and the gridded functions. So this block here, line 22, shows you how to do an interpolation call for a non-gridded function. And there's the plot that I was working on. Scrolling down here. All right, so here we have two positions. We have time, longitude, latitude, and height, because this is the neutral temperature variable that depends on height. This set 40 of a 4D coordinate followed by another 4D coordinate. And if you wanted to do multiple of these, you would just make a long list of these. So you're giving it two coordinates, two positions in 4 dimensions, and make that into a list and put that into the parentheses. And you get the interpolated values at those positions and times. Notice that in this example, I have two different times here, same longitude, same latitude, same height. You can do the same interpolation call with a gridded interpolator by simply giving the time coordinate a list of those two times, and then the single longitude, latitude, and height value, and you get the same values. So it's a matter of syntax, it's a matter of what you want to do with it when you're thinking about, well, do I want the gridded interpolator or not? So it's not a significant addition of execution time because the gridded interpolator is built on top of the non-gridded interpolator. It's up to you. All right, so that's the end of the Start Here tutorial. Please check out the next one for more information. Thanks.